Acid-base reaction. Between acids, we don't have reaction, and between bases, no reaction. When we mix any acid with any base, we have reaction. But this reaction depends on the nature of the acid and the nature of the base. The general rule, the reaction takes place between the strongest acid and the strongest base. Suppose we have a mixture of acids and mixture of bases, and we know that the reaction that takes place the first is between the strongest acid and the strongest base. So what are the steps to write the sequence of reactions acid-base? Step 1, increasing order of pKa, and we have two references, H2O, HCO plus of pKa 0, and OH minus, H2O of pKa 14. OH minus is the strongest base, and HCO plus is the strongest acid. Then we put the couples involved in the reaction. We put the couples involved in the reaction according to the data given. Then we determine the predominant species. Suppose in this figure, the predominant species are OH minus and HA. The reaction is advanced in the direction of gamma. So in this example, OH minus react with HA in the direction of gamma, so this reaction is advanced. If the reaction takes place in the anti-gamma direction, so this reaction will be limited. Then we write the reaction. For example, HA plus OH minus gives A minus plus H2O. We calculate the equilibrium constant of this reaction. In our example, K equal concentration of A minus divided by concentrations of HA and OH minus. So K of the reaction equal Ka over Kw. The value of K will indicate if our reaction is complete or not, or quantitative or not. In this example, the stoichiometry is 1, 1, 1, 1. So if K is greater than 10 to the power 4, so this reaction is a quantitative, or if K is greater than 10 to the power 6, so this reaction is complete. Suppose in our example, we have OH minus, HA, and HCO plus. OH minus is a base, HA and HCO plus are acids, so we have two reactions, OH minus with HA and OH minus with HCO plus. So we have to write these two reactions and calculate K for each reaction. If the reaction we wrote are of same stoichiometry, the value of K of reactions can be compared to know the sequence. If the stoichiometry is different, so we have a rule, the larger gamma is more advanced. So OH minus will react first with HCO plus, then if we have OH minus remained, it will react with HA. So we have two cases. Case 1, our reactions are successive. So reaction 1 starts and then reaction 2 starts, and this case is present when K of reaction 1 is greater 100 times than K of reaction 2. Or case number 2, the two reactions take place at the same time. So we have to add these two reactions to obtain the global reaction, calculate K global, and work on the equilibrium of the global reaction. Suppose we mix OH minus with HA and HCO plus. So two reactions are possible. OH minus plus HCO plus that give 2H2O, and K for this reaction equal 1 over concentration OH minus times HCO plus. So K of this reaction will be noted K1 equal 1 over Kw equal 10 to the power 14. The second reaction taking place is between OH minus and HA. So OH minus plus HA gives A minus plus H2O. K for reaction 2 noted K2 equal A minus concentration divided by OH minus times HA, and the concentrations are at equilibrium. So K2 equal Ka divided by Kw. Case number 1, so we have successive reactions. That means K1 is greater at least 1000 times K2. And to note, in our course, we use the order 100. And I explained before the difference. In the American system, they use the order 1000, and in the French system, they use the order 100. So in our course, we will use K1 greater 100 times K2. So reaction 1 proceeds, and then reaction 2 proceeds. So we have to work first on reaction 1 to find which is limiting and what is the excess and what are the products formed. So after we study reaction 1 and we do all calculation, we have to determine what are the new species present. So we have to do new balance of species. Then we proceed to reaction 2. In case number 2, suppose we mix two bases, B minus and A minus, with the acid HCO plus. So we have two reactions. B minus react with HCO plus to give HB and H2O, and K of the reaction is K1. And A minus react with HCO plus to give H2O and HA, and K of the reaction is K2. So we have to calculate K1 and K2. Suppose K1 is not greater 100 times K2, so the value of K1 and K2 are close. For example, in this case, the two reactions proceeds at the same time. So we cannot work on reaction 1 nor on reaction 2. We have to work on the global reaction. So we write the global reaction A minus plus B minus plus 2HCO plus gives HA plus HB plus H2O. K global for this reaction is very important to know if it's complete or not. So if the value of K global for this reaction is very high, that means this reaction is complete. So we have to work at T equal infinity to find, for example, the concentration of HCO plus, then to deduce the pH. And if the value of K global is very low, this reaction is incomplete. We have to work at T equilibrium and calculate the concentration of HCO plus at equilibrium in order to deduce the pH of the final solution. pH of a solution of salt. A salt is the product of the reaction between acid and base. For example, HCl reacts with NaOH to produce NaCl and water. So NaCl is a salt. The cation Na+ is provided from the base, and the anion Cl- is provided from the acid. So what would happen when we dissolve a salt in water? We say we obtain a salty solution, and this solution can be neutral, acidic, or basic. To know the pH of the salty solution or the nature of the salty solution, neutral, acidic, or basic, we calculate its pH. So we have two ways to know the nature of the solution obtained when we dissolve a salt in water. Method number 1 is to study the types of the initial acids and base that provide this salt according to the nature of the acid and the base, according to their strengths, strong acid or weak acid, strong base or weak base. We can know the nature of the salty solution when we dissolve this salt in water. The second method is to study the interaction with water of ions obtained after dissolution of salt. Suppose, for example, we dissolve NaCl in water, we obtain Na+ and Cl-. We study the interaction of Na+ with water, Cl- with water, and we can deduce the nature of the solution obtained. So method 1, to know the pH of the solution, we can study the types of initial acids and bases that provide this salt by reaction. If the salt in solution, we put in solution, is provided from the strong acid and the strong base, so the salty solution obtained is neutral. If the salt is provided from a weak acid and a strong base, so the solution is basic. And if the salt is provided by strong acid and weak base, so the salty solution is acidic. So method 1, we study the types of the initial acids and bases that provide the. If the salt is provided by a weak acid and a weak base, the salty solution obtained may be acidic or basic. It depends on the strength of this weak acid and this weak base. The method number 2, to calculate the pH of a salty solution, is to study the interaction with water of ions obtained after the dissolution of salt. For example, consider a salt Mn, the cation M+, and the anion N-. If the ion that interact with water give HCO+, the solution obtained will be acidic. And if this interaction release OH-, the salty solution obtained will be basic. And if the ion does not interact with water, so it would not release HCO+ nor OH-, this ion is spectator and the solution will be neutral. Now, how to know if the ion involved is spectator or not? Any ion involved in a couple acid-base means it interacts with water, so it's not spectator. Consider a salt NaCl in solution. Na+, the cation, is provided by the strong base NaOH. Cl-, the anion, is provided by the strong acid HCl. So the acid and the base that provide this salt are strong. In this case, the solution obtained when we put NaCl in water is neutral. We can use method number 2 to know the pH of the solution obtained. NaCl is a salt that dissociates completely to Na+ and Cl-. We don't have any couple acid base containing Na+, and the same for Cl-. So Na+ and Cl- are spectator ions, and the pH of the solution obtained is 7, and the solution is neutral. Consider a salt, sodium acetate. The acetate, which is the anion, is provided by the weak acid CH3COH. Na+, the cation, is provided by the strong base NaOH. So this salt is provided by a weak acid and a strong base. The solution obtained is therefore basic. We can use method number 2 to know the nature of the solution obtained. Sodium acetate dissociates completely in water to produce CH3CO- and Na+. CH3CO- appears in the couple CH3COH, CH3CO-, so CH3CO- interact with water. We don't have any couple acid base containing Na+, so Na plus is spectator. CH3CO minus obtained will interact with water to produce acetic acid and OH minus. So when we dissolve sodium acetate in water, we obtain OH minus ions, so the solution is basic. The pH of the salty solution CH3COO is therefore equivalent to the pH of the weak base CH3COO-, and we return to the pH formulas of the weak base where we have three domains. We compare the initial concentration of acetate with respect to Kb. If the initial concentration is greater or equal 100 Kb, so the formula applied, POH equal half pKb minus half log C, then we deduce the pH of the solution, where pH plus POH equal pKw. If we find, for example, that the initial concentration of acetate is not greater or equal 100 Kb, so we have to solve the second degree equation. Consider the salt NH4Cl in water. NH4Cl, the cation NH4 plus, is provided by the weak base NH4OH, and the anion is provided by the strong acid HCl. So this salt is obtained from strong acid plus weak base, and the solution will be acidic. Another method is to study the dissociation of NH4Cl. NH4Cl is a strong electrolyte that dissociates completely to NH4 plus and Cl minus. We don't have any coupled acid base containing Cl minus, so Cl minus is a spectator. NH4 will interact with water to give NH3 and HCO plus. So when we dissolve NH4Cl in water, we obtain HCO plus ion, and the solution is therefore acidic. So the pH of the salty solution NH4Cl is equivalent to the pH of the weak acid NH4 plus. We compare the initial concentration of NH4 plus with respect to Ka of the couple NH4 plus and H3, and if we find C greater or equal 100 Ka, so we apply directly the formula pH equal half pKa minus half log C. If C initial is not greater or equal 100 Ka, we have to solve the second degree equation. To note, how to know that the electrolyte or the salt is strong or weak, that means dissociates completely or dissociates partially. Any salt given without a value Ksp, this means that this salt is a strong electrolyte and dissociates completely in solution. And we will study in details the meaning of Ksp in the chapter solubility. Calculation of the pH of a solution of salt provided by a weak acid and a weak base. Suppose we have a salt Mn that dissociates to M plus and N minus, and M plus and N minus interact with water and are not spectator ions. So at t equals 0, we have N0 of Mn, 0 M plus, 0 N minus. Since the dissociation is complete, this reaction will proceed till t equal infinity, where we have 0 mn and we have n0 m plus and n0 n minus. Since the volume of the solution is constant, so we divided n0 by v0 and we obtain the concentration of m plus in the final solution is equal to the concentration of n minus in the final solution equal n0 over v0 equal c0. So when we dissolve Mn provided by a weak acid and a weak base, we obtain ions M plus and N minus of equal concentrations. Since M plus is not a spectator ion, it will interact with water to produce HCO plus, and K of this reaction is equal to Ka of the couple M plus. By the same way, N minus will interact with water to give OH minus, and K for this reaction is equal to Kb of the couple N minus. So when we dissolve Mn in solution, we obtain H3O plus ions and OH minus ions. If HCO plus in the solution is greater than OH minus, so that final solution will be acidic, and if OH minus is greater than HCO plus, the final solution is basic. To note that we start from the same initial concentration, so the quantity of HCO plus released from M plus and the quantity of OH minus released from N minus depends on the value of Ka and Kb. So to compare the final concentration of HCO plus and OH minus, we can compare Ka and Kb. If Ka is greater than Kb, and we started with the same initial concentrations, that means HCO plus in the solution is greater than OH minus, and the solution is therefore acidic. If Kb is greater than Ka, and we started by the same initial concentrations, so OH minus provided by N minus is greater than HCO plus provided by M plus, and in this case the solution is basic. And if Ka equal Kb, starting from the same initial concentration, we have equal concentrations in solution of HCO plus and OH minus, so the solution is therefore neutral. By this way, we can know the nature of the solution, of the salty solution, where the salt is provided by weak acid and weak base. This is a qualitative analysis, so we have to pass to the quantitative analysis to calculate the pH. We pass to the calculation of the pH of a solution of salt, for example CH3COO NH4, to note that this salt is provided by the weak acid CH3COOH and the weak base NH4OH. First method, CH3COO NH4 dissociates completely in solution to ions CH3CO minus and NH4 plus, and the concentration of these ions are equal to C0. Then CH3COO minus is not a spectator. It will react with water to give acetic acid and OH minus. So in this reaction, we have the acid and its conjugate base. So we have the couple CH3COH, CH3COO minus. We can apply directly the pH of Henderson, pH equal pKa1 plus log CH3COO minus divided by CH3COH, and this are the concentrations at equilibrium. By the same way, NH4 plus will react with water to give NH3 and HCO plus, and here the couple NH4 plus NH3 is present, so we apply Henderson, pH of the solution equal pKa2 plus log base over acid at equilibrium. To know that the dissociation of CH3COO and H4 produce CH3COO minus, which is a base, and NH4 plus, which is an acid. So by theory, a reaction will take place between the base and the acid. But since the reaction is highly advanced in the direction of the dissolution, so the reaction in the opposite direction is practically limited. Therefore, CH3COO minus and NH4 plus behave as free ions in the solution. So the pH of the solution can be determined by couple 1 or by couple 2. Adding these two formulas, we obtain 2pH equal pKa1 plus log acetate divided by acetic acid plus pKa2 log NH3 divided by NH4 plus. So 2pH equal pKa1 plus pKa2 plus log acetate in the solution times ammonia in the solution divided by acetic acid in solution times NH4 plus in the solution. Reaction of dissociation of acetate has a value K1 equal Kb of the couple equal Kw over Ka equal 10 minus 9.25. That means the dissociation of acetate is very weak, and we have small quantity of acetic acid formed. By the same way, the reaction of dissociation of ammonium in solution has a value K2, which is to Ka of the couple NH4 plus equal 10 minus 9.2. So the dissociation of NH4 plus is very weak, and we have also formation of small quantity of NH3. So since we are starting with the same initial concentrations and the dissociation of acetate and NH4 plus are very weak, so NH4 plus in the solution is practically equal 0, and acetate in the solution is practically equal 0. So NH4 plus equals acetate in the solution. By the same way, we explain that the formation of acetic acid and NH3 is practically negligible. So CH3COH in the solution is equal to ammonia in the solution. Therefore, in this formula, we can simplify by acetate and NH4 plus and by NH3 and acetic acid. So pH equal pKaE couple 1 plus pKa of couple 2, and therefore pH equal half pKa couple 1 plus pKa couple 2. This relation can be applied directly for a salty solution where the salt is provided by weak acid and weak base. For the solution of ampholyte species HA-, HA- is identical to CH3COO and H4 because HA- play the role of weak acid and the role of weak base since HA- is ampholyte. So by the same analogy, we prove that the pH of ampholyte solution or amphoteric solution is equal half pKa, where this ampholyte is acid, plus pKa, where this ampholyte is base. We can prove the formula half pKa1 plus pKa2, or the formula of the pH of salty solution obtained from weak acid and weak base, by another method. This method is the calculation of pH by following the steps. 1. What are the species present? We have acetate and NH4 plus from the dissociation. The presence of NH4 plus indicate the presence of NH3, and the presence of CH3COO- indicate the presence of CH3COH. And we have HCO plus and OH- and H2O. Second, the principle of the electroneutrality. The quantity of charge positive is equal to the quantity of charge negative. So NH4 plus in the solution plus HCO plus in the solution equal acetate in solution plus OH- in solution. The third step is to apply the mass conservation of species. Acetate dissociate to acetic acid, and the initial concentration of acetate equal C0. So acetic acid in the solution plus acetate remained is equal to C0. NH4 plus initial has a concentration C0 and dissociate to NH3. So NH4 plus remained in the solution plus NH3 formed in the solution is equal to C0. So we have this relation. The concentrations of CH3COH plus CH3COO- in solution is equal to the concentration of NH4 plus and NH3 in the solution. In step 4, we write the relations. We have the acidity constant of couple 1, acetic acid acetate, and of couple 2, ammonia. And we have also the water dissociation constant, Kw equal HCO plus times OH- in the solution equal Kw. Now we have to pass to the approximations. First, we neglect the autoionization of water since in most cases our solution is not very diluted. Second, we neglect HCO plus and OH- in the solution since our acid and base are of weak behavior. We have to remember that CH3COO and H4 dissociate to CH3COO- and NH4 plus. So if CH3COO- is a weak base of weak behavior, we would not have formation of a great amount of OH-. And NH4 plus is also a weak acid of weak behavior, so it would not dissociate to give HCO plus, so we can neglect HCO plus in the solution. And in this case, HCO plus is negligible with respect to NH4 plus since the dissociation of NH4 plus is very weak, and OH- is negligible with respect to acetate, since the dissociation of acetate is also very weak. So we obtain in relation to NH4 plus in the solution equal acetate in solution, and therefore in relation 3 we will have CH3COOH equal NH3. So 2 will produce 3. Combining these two relations, we will obtain Ka1 times Ka2 equal acetate times HCO plus divided by acetic acid times NH3 times HCO plus divided by NH4 plus, simplify by NH4 plus and acetate, NH3 and acetic acid, we obtain Ka1 times Ka2 equal HCO plus square, and therefore the pH equal half pKa of couple 1 plus pKa of couple 2.